Hi, I'm Toby Dewhurst, an ocean engineer with Kelson Marine. We're working with the U.S. Naval Academy, the University of New England, and Callentis Consulting to develop a validated, practical, finite element modeling tool for predicting hydrodynamic loads on large macroalgae farms. The hydrodynamics of flexible structures are complex, so our approach is to measure the mechanical and geometric properties of real kelp species, then build physical models of the kelp and test them in a combined wave and tow tank. From that data, we derived hydrodynamic coefficients, from which we constructed what's called a dynamic finite element model. What that means is we break every part of the farm, the kelp, the lines, the buoys, into small, finite elements, and at each instant in time, the software tool solves for the forces on each element and integrates those structures to compute the entire farm's response to waves and currents. We can then build finite element models of all kinds of farm designs and subject them to the maximum expected waves and currents for a particular site. We can predict things like maximum mooring line tension, or how far below the surface the kelp sags down when the farm deforms. We can also design for operational considerations, like how much force will it take to raise the line to the surface for harvesting. With this model in place, the biggest question for us as engineers was, does the tool give valid answers that we can use to design robust offshore farms? So we deployed a farm at the University of New England's site in Saco Bay, Maine, on the USA's northeast coast. This site is fully exposed to the Atlantic Ocean. The design conditions are a 1 meter per second current and a 4.2 meter significant wave height. Once the kelp was fully grown, we deployed load cells to measure the tensions in the mooring lines and simultaneously measured waves and currents at the site. We captured a storm event, and from that storm event, we extracted 5 different data sets, each with different combinations of current direction, current speed, tidal elevation, and wave height. And we simulated each combination. For comparison, though, we also looked at what predictions we would have gotten if we had used spreadsheet-level analysis, taking some basic static assumptions about the kelp. First, we looked at the answers we would have gotten if we had approximated the entire grow line with kelp as a single, rigid, flat plate, with the same total outline area as a grow line with biomass. And we found that that method would have seriously underpredicted the mooring tensions. On the other hand, using a more conservative assumption, we looked at what we would have predicted for these storm conditions if we had multiplied the total kelp blade area by a total skin friction coefficient and integrated the drag force over the farm. That approach would have overpredicted the mooring tensions by a factor of 4 or more. Finally, we simulated each measured combination of waves, tides, and currents in the finite element modeling tool that we've been developing. And the results almost exactly matched the measured tensions. The next question was whether this tool is practical for informing design choices. To evaluate that, we combined the dynamic model with a simple cost model for a farm. The cost model included capital expenditures and approximated total biomass yield based on usable grow line length and kelp growth as a function of average grow line depth. We then quantified the approximate biomass per dollar capex. And using a design of experiments framework, we quantified how various design choices, such as line spacing, mooring scope, buoyancy, and mooring line stiffness, affect the target metric, biomass per dollar capital expenditure. The surprising result was, if you look at the biomass yield in kilograms per dollar of capex over the design space, we can see how sensitive the optimal design is to choices of line stiffness, mooring scope, and how much buoyancy is installed on the farm. These results suggest that a carefully designed system can perform up to 3 times as well as our original design. And this is all done with simulations that can be run in a few days on a desktop computer. So now we have some confidence that our finite element approach is not only giving us valid results, but also has practical applications for designing novel offshore farms.